Okay, in this presentation we're going to look at the correlation coefficient and particularly a hypothesis test based on the Pearson correlation coefficient. So, in a correlation analysis based on a random sample of 10 values, that's an important detail there, 10 values, from a bivariate normal distribution, okay, just to sort of state that the Pearson is an appropriate correlation coefficient. Hypothesis test of rho less than or equal to 0 versus rho greater than 0. The null hypothesis is less than or equal to 0 and the alternative is greater than 0. Results in a probability value of 0.025. Now, before I continue, actually, I just remark that this is a one-tailed test. Okay? That's an important detail, actually. That's very important to pick up on. Calculate the value of the sample correlation coefficient. You may assume it's positive. Okay? So this is the test statistic for this test. So when you're doing this test, the test statistic is R times the square root of n minus 2 divided by 1 minus r squared. And it's a t random variable, t distribution with n minus 2 degrees of freedom. Okay, yeah, so the degrees of freedom, nu equals n minus 2, in this case would be 8. Okay, so if the p-value for the one-sided test is 0.025, then the observed t-value will be 2.306, and from that's determined from that's a sort of critical value determined from statistical tables, okay, like some small sample tests. So the test statistic will be 2.306. n minus 2 is 8, so we're dealing with 2.306 equals r times the square root of 8 divided by the square root of 1 minus r squared. Okay, now essentially what we have to do here is just do a bit of calculator work. Squaring both sides and algebraically rearranging, we would get 5.318 times 1 minus r squared equals 8 r squared. That's squaring both sides as well. Okay, and just working that out, r squared is 5.318 divided by 13.318, and that works out to be 0.3993. Get the square root of that, and that is the correlation coefficient that we're looking for. We would get 0.632. Okay, so that's how we do that one. Now, I got a little treat in store. We're going to look at the Fisher and Zed Transformation. Okay, so this is a different approach looking at this test. So essentially what I have here at the top is a bit of theory about it. If we have a pair of variables have a bivariate normal correlation, a bivariate normal distribution with correlation, and the pairs are identically distributed, then Z is approximately normally distributed with mean 1/2 of log of the 1 plus rho divided by 1 minus rho, and the standard error is given as 1 over the square root of n minus 3. So there's essentially a bunch of stuff there to look at. This is the key thing actually here. Okay, there's a lot of theory going on in this. So essentially the test statistic is here. Okay, so, and also it's a Z random variable, standard normal random variable. So the test statistic is square root of n minus 3 divided by 2 times the log of 1 plus r, where r is the observed value, divided by 1 minus r. Okay, so what we have to do here is try and figure out what r is. Now just remember, the p-value is the standard way of determining p-values, okay, the conventional way. Just recalling that a lot rides on the fact if it's a one-tailed test or a two-tailed test. That's why I sort of said it was very important earlier on, okay, that this is a one-tailed test. Okay, so That's the theory part taken over, or dealt with. An alternative approach is to use the Fisher and Zed Transformation. So this is me answering the question now. And that's me using the test statistic there. Okay? Now, I'm noting the p-value is 0.025. Okay? And I also note that in this case, we're going to use the standard normal distribution, the Z distribution. So in this case, the test statistic should work out to be 1.96. Okay. So the test statistic is 1.96. Essentially what I'm going to do here is just rearrange everything. N square root of n minus 3 is the square root of 7. Okay. Essentially what I'm going to do is bring all of this over here and multiply it by 1.96. So the square root of 7 divided by 2 becomes 2 divided by the square root of 7 times 1.96. That gives us 1.4816. Okay. So what we do is exponentiate both sides, which is to say transform the log of something into exponentiate it essentially. Just get the exponential of both sides. So the exponential of I'll just make that a bit bigger, is pretty much 4.4 bang on. Okay, so what we have here now is 1 plus r divided by 1 minus r, and that's equal to 4.4, and essentially it turns into a very straightforward calculation. Okay, and in this instance we get a correlation coefficient of 0.63, which is very, very close to how we did it in the first half of the video there. Okay, so that's two different approaches for the same question. There's a lot going on, the Fisher transformation and so on. So I think we'll leave it there.